My name's Ifan Stephens. I'm the reader in electrochemistry in the Department of Materials, and also leader of the Electrochemistry Network. So I'm going to be talking very much along the same lines as what Anthony's been talking about, but my talk is going to be a little bit more about kind of common pitfalls in measuring electrochemical kinetics. So I'm going to start with a kind of very personal anecdote about what kind of talking about why I find measuring kinetics and doing it kind of correctly is important, how it affected my own research, and then go on to more detailed examples of how to do this. So back in 2009, I was a postdoctoral researcher in the Technical University of Denmark, and at the time, I was working with theorists, Jens Snerskov, Jan Rossmeisel, Heiner Hansen, and Jeff Greeley, and they predicted using density functional theory calculations that so we were looking at oxygen reduction for fuel cells. We wanted to look at alloys to decrease the amount of platinum, so we wanted to look for more active catalysts for oxygen reduction. And they predicted, I won't go into detail about this, but they predicted that the platinum yttrium, platinum scandium, and palladium yttrium were very active catalysts for oxygen reduction from the theoretical calculations. They wanted me to do the experiments. I'll go into more detail about the kind of fundamental insight we got from these experiments later on when I talk about combining experiments and theory in my later lecture. So essentially, this is a process we went through. We had predictions from density functional theory, then we made a smooth polycrystalline alloy electrode, it's about 5 millimeters in diameter. Then we sputter cleaned it under ultra high vacuum conditions. Then we put it into rotating disc electrode setup, as similar to the one that Anthony described earlier. We tested it in perchloric acid. So the first catalyst we actually tested was palladium yttrium. Initially, we measured oxygen reduction reaction on it, and it looked like it was pretty active, and we also tested platinum, and it looked like the palladium yttrium was actually more active than platinum. So this was really exciting because we thought palladium that would be really good if we could get a palladium-based electrode, because palladium is usually less active than platinum, but if we could get palladium to be more active. And we got really excited, and all the theorists got excited and said this proved that the theory was correct. And anyway, then I started trying to make sure that my platinum agreed, the benchmark platinum I used agreed with the literature, and I found out, to my disappointment, actually, that the platinum activity was actually lower. So the platinum activity that I'd already measured was lower than the state of the art in the literature. And actually, so I used my own platinum experiments were really inactive. And palladium yttrium only performed better than the really inactive version of platinum that I'd done. So basically, I'd done all the experiments wrong on the benchmark platinum. So I was really disappointed, and I thought, okay, I want to try these other platinum-based catalysts, but first I want to really get the platinum measurement right. So I went through that process, and then I went on to measure platinum yttrium, platinum scandium. And actually, it turned out that platinum yttrium in particular is much more active than platinum. This time, this platinum, so the current is a function of potential, the kinetic current, and this time, actually, the platinum yttrium was the most active catalyst tested in this way, reported in the literature. I was really excited. In fact, the first time I showed this in a conference, another person from another research group who's well known in the field actually criticized me and said, your results are rubbish. This is nonsense. Your platinum activity is really inactive. And I said, actually, my platinum is more active than your catalyst. So we knew that we'd done it right. So it was really, if I hadn't gone through the steps of actually making sure that we could get reproducible data and making sure that what we did was comparable to literature, we wouldn't have been able to prove that this platinum yttrium catalyst was as active as it was, and we wouldn't have had credibility from the wider electrochemistry community. So benchmarking, the main take-home message I want to say about this is the benchmarking catalyst activity in a correct way and doing it in a comparable way to the literature is really important. So, and the journal editors are paying increasing scrutiny to these type of issues. For example, if you look in ACS Catalysis from 2017, the editors have written editorial articles saying about best practices in the pursuit of topics in heterogeneous electrocatalysis. One of the points they make in this article here is that they strongly recommend against using platinum counterelectrodes, and they actually say that in ACS catalysis they will refuse or reject any papers if you use a platinum counterelectrode automatically, at least if you're looking at non-precious metal catalysts. So that's the last thing you want is to get your paper rejected because you're using a platinum counterelectrode. You have to redo all the experiments. So a lot of what I'm talking about, at least in the first part of the talk today, is based on a review paper. I've forgotten to put the date in here, but it's from 2019 that I did with several researchers from Nanyang Technological University, MIT, and Helmholtz Institute in Berlin, and including one of the researchers from MIT, Reshma Rao, is now actually at Imperial College. So in summary, what I'm going to be going through first is talking about electrochemical cell, then talking about how to measure surface area, which is a very, very important thing if you want to measure reaction rate. Also talking about how to benchmark stability, and also talking about some other reaction-specific considerations. So what I'm showing today is very relevant, not only for those looking at electrocatalysis of low-temperature fuel cells and electrolyzers, like in my own research group, but also it's interesting for people looking at photoelectrochemistry, corrosion scientists, aqueous batteries, and also even enzymes. So if you look at a PEM fuel cell, so this is a cross-section that I got from Peter Strasser. It's quite, what you can see is that you've got an anode on the left-hand side and a cathode on the right-hand side, and then you've got a proton-conducting polymeric membrane in the middle. You see the structure is quite complex. So the ideal way to test a catalyst, of course, would be to test it in a fuel cell, but it's quite difficult to do that for each and every new catalyst that you test. So you often want to look at more modeled, more simple conditions, such as the ones that Anthony described in his previous lecture. And in particular, we usually use 3 electrode cells with a liquid electrolyte. So they're a lot easier to optimize in many cases. And the one most commonly used one is rotating disc electrode. As Anthony mentioned, it does have its drawbacks. In particular, it can go to very, very high rates, but it is very easy to optimize, and it's very well documented how to use it. I want to go into more detail right now about it. And of course, when you use reference electrodes, but I would say for electrocatalysis, maybe the most useful reference electrode is a reversible hydrogen electrode, or RHE. So in practice, what that is a reversible hydrogen electrode is a platinized platinum electrode in electrolytes of choice, and it's saturated with 1 atmosphere hydrogen. And the hydrogen evolution, hydrogen oxidation is at equilibrium. So the reason why this is actually a very, very convenient scale is if you look at a number of different reactions, so also including oxygen evolution reduction, CO2 reduction to CO, CO2 reduction to ethylene or ethanol, or even nitrogen reduction, that all these reactions often take place at a specific potential on the RHE scale, and this potential is pH independent, because the reason for that is because you've got the same number of protons and electrons for each of these reactions. So that means the thermodynamic potential for the reaction is pH independent on the RHE scale. So you can see that, for example, for oxygen evolution and oxygen reduction, on the RHE scale is the difference between this line and this line. So you can see the oxygen evolution, oxygen reduction changes potential on the SHE scale is the same amount as the RHE. So it's always oxygen evolution always occurs at 1.23 volts. So if you know the RHE potential, reversible hydrogen electrode potential, you can get accurate measurement of potential for all the above reactions. So often you can get the reversible hydrogen electrode potential from tabulated values in literature relative to different reference electrodes. However, in my own experience, it's better not to estimate it. It's better to measure it. Ideally, especially if you're looking at a reaction like, for example, oxygen reduction, where often you want to show that your electrode is a few millivolts, has a few millivolts less over potential than another report in the literature, then a few millivolts becomes really important. So really, that ideal way to measure the RHE is to measure it for every single experiment. So you can either make your own reversible hydrogen electrode, or you can buy a commercial one. So the other thing related to potential as well is that, of course, you always have an ohmic resistance in series with the actual other parts of your with your working electrode. And it's important to actually be able to know what the ohmic resistance is. The ohmic resistance due to the electrolyte. It could be also due to contact resistance, because otherwise the potential that you're applying won't be the same potential as that which is at the working electrode. What we're really interested in knowing is what the potential is at the working electrode. Things like the potential of the electrolyte and the contact resistance are more cell dependent, so it's not reproducible between different groups. So you want to remove any ohmic drops from the actual measured potential. And probably the best way to do that is to carry out an impedance spectroscopy measurement. Essentially what you're doing is you're applying an AC potential on top of the potential you normally apply, and then measuring the AC current. You'll find out more about impedance spectroscopy in Sam Cooper and Jason Riley's later lectures. And typically what we measure is, so this is an imaginary component of the impedance. This is the real component. It's typically what we need to measure to obtain the compensated cell resistance is to measure the high frequency intercept. The problem is, what tends to happen is at very, very high frequencies, we also start to see impedance of components outside the electrochemical cell. For example, the inductance of the cable. That's what's in this green box here. So one way of getting around that, instead of making a Nyquist plot, is to make a Bode plot. So the Bode plot essentially shows the amplitude of the impedance and the phase as a function of frequency. The information is equivalent to Nyquist plot. So that you see the total amplitude of the impedance is the blue, and red you've got the phase. So recall that phase angle resistor is 0 degrees, a capacitor is minus 90 degrees, and inductor is plus 90 degrees. So what we can see is we can obtain the uncompensated cell resistance at the highest frequency. So this is the frequency is going up here. So the highest frequency where the phase angle approaches 0. So that would be here. And at frequencies above that, above 100 kilohertz, we can see that we actually picked up the cable capacitance and inductance. So this is actually irrelevant to the electrochemical data. So I wouldn't, if you were talking specifically about the electrochemical data, I wouldn't even plot this part here because it's not relevant. For more info on impedance, see lectures 7 and 8 by Sam Cooper and Jason Riley. So the effect of actually correcting for ohmic drop is shown here. So essentially the corrected impedance is shown in red. Sorry, the corrected current function potential is shown in red, and the measured is shown in black, the original data. So you've taken away the current times the resistance, and you can see that the ohmic drop increases as you go into more and more positive potentials. Make sure you use the current in units of amps, not current density. And you can usually make this correction either by doing it after the measurement. The disadvantage of that is that the actual potential applied, especially when you go to high currents, is not the potential you want to get to. Or you can use online compensation. The disadvantage of that is usually you get a potentiostat oscillation. But if you're interested in these details, or more deep discussion of a lot of these details, I suggest you have a look at the paper I cited a few slides ago in Advanced Materials. So, as I mentioned, counter electrode often a choice of counter electrode is often important, especially if you use the wrong counter electrode in certain journals, they won't even look at your paper. So the problem is, so usually when you choose a counter electrode, what you really want to do is to get a counter electrode that is inert and that doesn't interfere with the reaction occurring at the working electrode, and it can pass as much current as possible. But even a platinum counter electrode is generally quite stable. It can dissolve somewhat and redeposit at the working electrode. And let's say if you are, imagine you are looking at a relatively inactive catalyst for hydrogen evolution. If you dissolve the if you end up accidentally depositing even small amounts of platinum, you can make the catalyst look a lot better than it really is. So that's the problem. So contaminants of platinum can be really counterproductive. An alternative would be to use gold. Gold is generally more inert and then generally less catalytically active, especially in acid solutions. But even in alkaline media, gold can be very active, for example, for oxygen reduction. And so using a gold counter electrode is not necessarily a good idea. Similarly, if you're doing CO2 reduction in neutral media, the gold can dissolve and redeposit at your working electrode, and gold is a pretty good catalyst for CO2 reduction to CO. Another alternative is a glassy carbon electrode. That's stable up to about pH 13. If you go into very, very alkaline solutions, even a glassy carbon will corrode. Sometimes it might even make CO, which could also contaminate the CO as a catalyst poison, so it could poison your working electrode. Another way of getting around problems with the counter electrode is to use something that can separate the counter electrode compartment from the working electrode. For example, you could use a hydroxide conducting membrane or a frit, and this would prevent deposition of species from the counter electrode at the working electrode. Of course, apart from the actual the materials that electrodes are made of, it's also important to consider what cell material you're using. Anthony already alluded to this. Generally, in acid media, I'd only use a glass cell. However, in alkaline media, glass cells often corrode. You leach out species such as silicon and lead, and this can poison catalytic reactions. We found, in my own group, we found poisons, for example, CO reduction in alkaline media. We found that the copper becomes much less active with time, and that's essentially because we're building up silicon oxide at the surface. And others have found similar results on platinum-based catalysts as well in alkaline media. An alternative would be to use PTFE or Teflon cells. They don't corrode in alkaline media. The only problem, they're fairly porous. So often if you have contaminants around, they get stuck and they'll leach out in the next measurements. Also, they're not transparent. But PTFE cells are not transparent, which can be a pain if you're used to working in glass. Some of my former colleagues at Technical University of Denmark, they proposed instead to use a PFA. And this is some cyclophotometers they did of copper single crystal in PFA relative to glass. And they found that they see much sharper peaks, and they attributed this because they think that the PFA is a lot cleaner. Generally, cleaning itself is also really important, especially if you're looking at very low surface area electrodes. So typically what you could, for example, you could pre-clean by soaking glass cell in concentrated sodium hydroxide solution. And then to get rid of organics, you can use no chromics or Pirania solutions. These are very, very hazardous, very, very oxidizing solutions, so make sure you make a proper risk assessment before you do it. And so a Pirania solution, for example, is a concentrated sulfuric acid and hydrogen peroxide. And And then once you've soaked it for at least 24 hours in these solutions, then you need to soak in several washes of really, really pure water. And in addition to actually making sure that you have a very clean cell and making sure that you have very clean water, you also need to make sure that electrolyte is pure. Typically, for at least if you're looking at potassium hydroxide or perchloric acid, I always use Merck Super Pure. It's quite expensive and has a very long lead time, up to about 2 years. So typically the way we get around that in my group is we try and stockpile it as much as possible. So we always have about 10 bottles of these electrolytes. Otherwise, and make sure that it's happened to me a few times over the past 10 or 15 years that they've said there'll be a 2-year waiting time before you can get the next batch of perchloric acid or potassium hydroxide. Other electrolytes, sometimes, so apart from using the right brands, Merck Super Pure, if you look at electrolyte composition, it's worth bearing in mind that some electrolytes might interfere with the reaction of choice. For example, sulfuric acid tends to block active sites, especially in platinum. So that's why we use perchloric acid, because the perchlorate anion doesn't absorb so strongly on platinum. Unbuffered solutions you can use sometimes, especially if you're looking at neutral media. Sorry, I'll say that again. If you're looking at reactions that occur in neutral media, you can either have buffered or unbuffered solutions. Problems with unbuffered solutions is that, for example, if you're looking at potassium perchlorate, potassium sulfate, potassium nitrate, is that what will tend to happen is you'll get local changes in pH at the surface of your electrolytes, and that will mean that actually you'll have you'll shift the effective reversible potential for the reaction. That's something you don't really want to happen. Alternatively, you can use buffered solutions, but often the species are used to buffer and hold the pH more stable. For example, a phosphate, they can also poison electrodes in a similar way to sulfate anions. So they can cause a lot of artifacts as well in the measurement of actual pH dependence. So what could be an apparent pH dependence would actually be due to anions from the electrolyte causing a change, blocking active sites. Similar, people have also noted the cation also has a strong effect in many reactions, including oxygen reduction or hydrogen evolution. Another thing to bear in mind is that metallic impurities can often accelerate reactions. For example, iron cations, they intercalate into nickel hydroxides electrodes, and they accelerate oxygen evolution. And similarly, for hydrogen evolution, cobalt and nickel impurities accelerate hydrogen evolution. And these cobalt, nickel, and iron impurities are really, really present almost even in really, really pure electrolytes. So it's worth bearing in mind that some of the effects you might be observing are due to these impurities from the electrolyte. So next topic I'd like to talk about is surface area. And this is really, really important topic, especially for those working on measuring reaction rates. So especially because ideally when you're looking at new materials, so there's two ways you can accelerate a reaction. Either you have much higher surface area, or because you have an intrinsically active material, because and it's important to be able to distinguish these two effects, especially if you want to do fundamental studies or to get fundamental insight into what is an intrinsically active material. So there are different ways of normalizing reaction rate. So you have geometric area. So that's just essentially, this is probably the more, when you're looking at an electrolyzer or something like that, this is probably how you're quantifying the performance of the electrolyzer in terms of you're normalizing reaction rates to the overall geometric area. However, if you have a catalyst, is often not flat, especially in a real device, so it can be quite corrugated. So then what you should do instead is to normalize according to the specific activity normalized to the surface area of the catalyst. So that would correspond to this profile here. Alternatively, especially if you're looking at very precious metals, what you should do then, you want to, for example, if you're looking at platinum-based catalysts, you want to minimize the amount of platinum. So you often normalize the currents according to the mass of the platinum. That's called the mass activity. So there's a few different ways of normalizing catalyst activity. So, so I'm going to elaborate now on trying to how to measure the catalyst surface area so we can get surface-specific activity. So the classical way to do that, for example, on a platinum catalyst, is using cyclic voltammetry. So you're cycling up the potential up and down, and then getting a current as a function of potential. So on platinum, the classical way of looking at this is that, and I'll elaborate in a moment to explain this is not quite right. So you have essentially three features. So you have at very negative potentials, you start to get, so remember negative, this will be a negative current here, and this is a positive current. And a negative current, the potentials, you start to absorb hydrogen, and then at positive potentials, you desorb the hydrogen. It hasn't shown, we haven't got the zero in here, but the zero current will be around here. And then, so when you get up to about this potential, about 0.5 volts, you no longer have any hydrogen at the surface. And then the current you get is when the electrode behaves essentially like a pure capacitor. Then you go to more positive potentials, then you start to oxidize water to make OH or oxygen at the surface. So essentially, what a lot of electrochemists do, and I also do this quite often, is that you assume then that this, you can integrate the charge like I've done here, and this charge corresponds purely to a hydrogen absorption, and you assume that it's actually if you this is based on polycrystalline platinum, so it's a very smooth disk, and then you assume that you can do the same kind of integration on a nanoparticle as well, where you don't know where it's not smooth, and then use this. And then by integrating this charge, you assume, you try and gauge what the surface area is. And this is usually a reasonable approach, but it's not actually always very accurate. So even if you look at kind of very single crystal surfaces, so for example, platinum 111, and what you'll see in this region where hydrogen absorbs, or where we think hydrogen absorbs, actually the charge varies enormously depending on the surface. So for example, if you look at platinum 111, this is atomically smooth surfaces, remember? You have about 144 microcoulombs per centimeter squared in this region. On a stepped platinum surface, it's 220 microcoulombs per centimeter squared. And then on an alloy surface, this is platinum from nickel alloy, but the surface is pure platinum. You have 80 microcoulombs per centimeter squared. Even though the actual surface area is always the same, the actual charge varies enormously. So it varies by up to a factor of 2.75. So actually, this assumption that this charge here is independent of the surface termination is not actually correct. Part of the reason for this is that in the region which we usually assign to hydrogen absorption, at least on other surfaces, let's say if you look at stepped platinum surfaces, or some platinum 110, it's not actually purely hydrogen. You also have oxygen and OH absorbing where hydrogen desorbs. So that's one of the reasons why you can see a much higher current here. Also, you might get sulfate co-absorption. That also complicates things. And cations actually can co-absorb in alkaline media. So that also complicates how you actually, the charge you end up getting out of these measurements. So another alternative way of doing it is actually comparing the double layer capacitance instead. So again, so the double layer capacitance, recall, is this area between 0.4 and 0.6 volts. And what we can see is that the double layer capacitance can change by a factor of up to 1.8 as well. So this is this region here. So that means that actually the double layer capacitance, it gives you a rough approximation of what is roughly proportional to surface area. This only gives you an order of magnitude value. So let's say if you see small changes in double layer capacitance between two different materials, it's probably doesn't necessarily mean that the surface area is very different. Only if you see really, really large differences, I would say like on the order of magnitude, can you be really certain about that. And so yeah, again, double layer capacitance is only a rough estimate. If you want to look at accurate measurements of measuring double layer capacitance, I suggest you have a look at this paper here from Marcel Rich. So another alternative to measuring double layer capacitance, or to measuring hydrogen absorption, is to actually use CO stripping. So essentially, what you do is you take your working electrode, you saturate the solution in 1 bar CO, holding the potential about 0.1 volts, and then you saturate it with argon to remove all the CO from the solution, and then you strip off the CO, and then so you essentially get this reaction. So you have and the star denotes an absorbed species. So you have a CO then reacting with water, getting oxidized, leaving CO, empty species at the surface, and you get CO2 formed. And so you're essentially measuring the charge used for making CO2. And a lot of electrochemists assume this charge is independent of alloying or surface orientation, and they use this to actually measure, again, what the surface area. This, again, this assumption is not always correct. We found actually a lot of detail about this is actually when we looked at different copper alloy surfaces. We particularly look at this kind of copper near surface alloy, where you have pure platinum surface, but with copper and second surface layer. So we can actually change the saturation coverage of CO and platinum by a factor of 2. Also, another thing to bear in mind is often when you add CO to a platinum surface, often causes restructuring of the surface, and that can also cause some artifacts in the measurement. So just by doing the CO stripping measurement, you can actually induce changes to the catalyst surface. Another method we found actually on the same copper near surface alloy as the single crystal, we found actually it worked better actually if you used a method that Anthony Kusunak had developed, originally for platinum ruthenium alloys. There, what you do is you essentially electrodeposit copper above the bulk dissolution potential, and you do what's called an underpotential deposition. So you deposit up to a monolayer of copper, and you won't deposit much more than a monolayer of copper because you're not at the potential bulk copper forms. And then you desorb the copper and measure the stripping charge. And we found that actually for these kind of gave us more consistent data than actual CO stripping. Anthony's also used other probe molecules or probe species. For example, an iron-based catalyst, he's used NO absorption and then NO stripping in the form of ammonia as a way of measuring number of active sites. So that's another method. If you're interested in that, you can have a look at this paper here. So apart from actually using electrochemical methods, another way you can do it is using the BET method. And that essentially what you're doing is physically absorbing nitrogen on the surface. There's plenty of different facilities available I know of at least 3 BT instruments, imperial in chemistry, chemical engineering, and materials. And you can do this very versatile method. You need a certain, a high surface area material to do it. And by physically absorbing nitrogen, you can measure surface area. And here's actually a plot comparing electrochemical surface area measured from AA capacitance versus BT surface area. And you can see there's not always a strong correlation between the two. Part of this reason is that when you're often measuring electrochemical surface area, actually, especially when you're looking on oxides, so this plot's mainly showing oxides, is that you're not only absorbing protons at the surface, you're actually the oxides has a lot of capacitance in the bulk or the subsurface. You're intercalating protons in and out. So you're not actually necessarily measuring a surface area. So this axis is actually wrong. Even though, for example, if you're looking at catalysts, usually it's the surface atoms that are active sites. So yes, so once you've actually measured the catalyst surface area, then you can actually make these kind of plots where you look at measuring the current. So you've got the current as a function of potential. Tafel plot for a number of different catalysts. Where this is and then you can compare different catalysts either according to the specific activities, normally as the surface area of the or the mass activity. So these data here are all based on rotating disk electrode measurements, and these most commonly used ones in the field. However, as Anthony mentioned before, sometimes rotating disk electrodes have drawbacks, in particular if you look on this plot here, we're comparing rotating disk electrode studies to real fuel cells, and we found that actually some of the really, really active catalysts have been reported in the literature. For example, is platinum-nickel nanoframes. When they're measured in rotating disk electrode, that's the light blue here, and then when we measure them in actual fuel cell, you see much lower performance. So this calls for actually testing catalysts in more realistic conditions, for example, using a lot of the methods that Anthony described earlier, like the floating electrode method. So we found actually, for example, we found some very interesting catalysts for oxygen reduction to hydrogen peroxide using, for example, platinum mercury catalyst. We found gold worked pretty well. And then when we actually tested it in a membrane electrode assembly, what we found is actually the catalysts that worked most well, like the platinum mercury, worked really badly in an actual real device. So what we found is actually worked better was to take gas diffusion electrons, submerge it into a stagnant electrolyte, and we found, especially when measuring selectivity for oxygen reduction, that actually was more representative of a real device, so the MEA, than the rotating ring disk electrode setup. So it is important to bear in mind that what actually works well in the actual rotating disk electrode setup, a rotating ring disk, doesn't always work well in a real device. So I'm going to go on briefly to oxygen evolution reaction. So here's a polarization curve of a state-of-the-art PEM electrolyzer. So so you've got the potential as a function of current, and the overpotential is the difference between the purple and the green line. And almost all the overpotential is due to oxygen evolution. That's why studying this reaction is important. And usually you'll use iridium-based catalysts for oxygen evolution. You can also use ruthenium. And here's what showing how cell potential changes with time for ruthenium and iridium. And you can see actually ruthenium actually works better at short times. So this is at constant current. And then what tends to happen is over longer times, you start to see the degradation in the performance. So the reason for this is essentially under conditions where these oxides catalyze oxygen evolution, you have very, very positive potentials. And in addition to actually getting oxygen evolution taking place, you actually start to oxidize the ruthenium or the iridium. So you have a side reaction of iridium or ruthenium dissolution. So you're making both, especially in the case of ruthenium, you tend to make ruthenium cations at the same time as evolving oxygen. So really, the other thing worth bearing in mind is what this shows is usually when we're doing a measurement, we don't have hundreds of hours to spare in our university-based labs, we usually want to do a measurement for an hour or two. So how can we probe this kind of very important degradation in short-term lab tests? So when we've done in the past, actually trying to measure dissolution rates, and we've done this in two different ways. One is either using electrochemical quartz crystal microbalance, and there essentially what you have is a quartz crystal coated with gold, and you're measuring, and then we put different catalysts on top of that, and then that and looking at the change in the frequency. As a function of time, and this gives you an idea if you change the amount of mass at the surface. Another different way you do it is using inductively coupled plasma mass spectrometry. Then you can quantify the amount of dissolved products you produce. So what we actually did an experiment where we made ruthenium oxide catalyst. We started to deposit it onto one of these quartz crystal microbalances. And then we measure the current as a function of time. And so what we could see is actually after about 2 hours, we get actually very, very stable electrochemical performance. And similarly, when we actually measure if we hold a constant current, measure potential, we see a very stable potential with time. However, when we actually then measure, if we actually measure the mass losses using quartz crystal microbalance at the same time, we see that actually, even though we see a very, very stable electrochemical response, we actually see there's a constant loss of mass on both surfaces. This is about equivalent to about 1 nanometer per hour. So that would mean that essentially, even though the actual corrosion current is about 4 orders of magnitude lower than the oxygen evolution current, the film is a 40 nanometer film, would only last about 30 hours. So really, what this shows is actually when you're trying to measure stability, if you want to test if you only test the catalyst for 2 hours, purely electrochemical measurements are insufficient. You really need to actually have a separate way of measuring the dissolution rate. So I would say the best way to do this is actually the easiest way and most versatile way is usually using ICP-MS. We've got facilities for that both in chemical engineering and in chemistry, and measuring how much metal ions are in solution before and after the reaction. Another way you can actually measure corrosion products is measuring what gases are produced. So we have a method at the Royce Institute in White City. We have an on-chip electrochemical mass spectrometry, which anyone in Imperial can use. Essentially what that does, you have a working electrode, and you have a very thin layer of electrolytes, and any gas phase species produce the working electrode go to a mass spec, and then you can measure these with really, really high sensitivity. So we were actually working with Liam Tran and Cern Scott and Magda Titrici and Ana Jorge Sobrido from Queen Mary University. We actually looked at some lignin materials that they'd been looking at, and because lignin is sometimes used as support for catalyst for oxygen evolution, and we tested the material under oxygen evolution conditions. So this is a current we got as a function of potential. I've seen in some papers people sometimes look at carbon-based materials as catalysts for oxygen evolution, and they see some similar current, and they start to see an onset of current above 1.2 volts, and this is around the thermodynamic potential for oxygen evolution. They see an onset of currents, and they say they've got a very low onset potential for oxygen evolution. So we actually could prove whether that's really the case by actually measuring the gas that's produced. And what we found is actually here, so this is a signal at the mass spec. What we found is actually that the signal for oxygen actually goes down, but what we have instead is a signal for CO2 going up. So this is essentially the carbon corrosion. We're making CO2 in the gas phase, and we're not actually producing any oxygen, because as I said, we're actually seeing a decrease in the oxygen background. So So this is another method apart from the kind of measuring. So you can use metal, you can measure metal cations using ICP-MS, or you can use electrochemical mass spectrometry to measure the gas phase products formed. There's also another example of this in this paper here, where they look at ruthenium-based catalysts, and then they can see both oxygen evolution and CO2 evolution in the same catalyst. So, sorry, my computer seems to have crashed. I don't know what's happened. I'm running out of time, so I won't go for I won't talk for too much longer. I wanted to mention briefly that there are other reactions that, like for example, if you're doing CO2 reduction, then typically it becomes even less. So I've talked already about when you're looking at oxygen evolution, sometimes that you might have side reactions like CO2 evolution. And when you're looking at the reaction like CO2 reduction, then the actual reaction you're interested in can actually fork off into many, many, many different pathways. For example, if you're looking at benchmark catalysts for CO2 reduction, the most studied catalyst is copper. They make 16 different products. So to quantify the products, you definitely can't rely on electrochemical measurements alone. You need both electrochemical measurements, at least 2 different analytical techniques. For example, gas chromatography and nuclear magnetic resonance spectroscopy. You need to balance the charge of the amount of products formed, and you need to explain if you have any unaccounted charge. It's very similar as well if you want to look at nitrogen reduction to ammonia. In my group, we're looking at that. And there are a lot of people claiming to reduce nitrogen to ammonia, but what we actually found was they're actually looking at contamination. I won't go into detail about that. The main point I wanted to say is you need to use isotopic labeling in a quantitative manner if you really want to prove you can do it. So I've come to the end of my lecture now. So main point I want to make is that cleanliness is really, really important. It's paramount. So be mindful of all contamination that might be present in your cell, whether it's coming from the electrolyte, from the cell material, or from the other working electrodes, or the counter electrodes. Ensure that you can match the best performance in the literature. Don't use a substandard benchmark. There's always room for improvement, even for benchmark data. You can make your own benchmark that will be adopted by other groups. You should calibrate the reference electrode potential very carefully. Always regularly check your benchmark experiments to check your setup is not contaminated. And be aware of differences between model experiments and real-life conditions. Anthony elaborated on a lot of these earlier. And if you want to find out more information, see the papers I've actually cited on the different slides.